Circuit analysis. So this is a second big five topic, right? So let us quickly rate these. How do you guys rate Kirchhoff's laws? Easy. Some circuits, guys, can be difficult. I would rate it as a medium, primarily because I used it as a benchmark, right? I used it as a benchmark that this is a medium level difficulty. Series parallel equivalent circuits, easy, agreed. Thevenin Norton, medium. Nodal loop analysis, that's basically for KVL, KCL, that's fine. Waveform analysis, it can be a little bit tricky as well. So let's call it medium. Phasors are pretty easy. A couple of things that you need to remember there. Impedance can be a little bit tricky, but let's just call it easy, right? Some students mess up the reactances. Some students don't recognize that this is omega L, okay? That this is not equal to j omega L. And we've discussed this several times. Impedance of an inductor is equal to j omega L and things like that, right? Susceptance and whatnot, everything is defined, so you don't need to memorize anything, okay? So you can see that circuit analysis is not a walk in the park. Having said that though, NCA sample exam, how many of you have started attempting problems from the NCA sample exam? When you go through the NCA sample exam, after going through the live training and on demand, for circuit analysis at least, it does look like a walk in the park. So super easy from the NCA sample exam, super easy. So the way I've prepared you guys for circuit analysis, and I was pretty transparent about it, sections that would pay dividends in PE power, we went deeper in them, right? Engineering economics, for example, we did 2 sessions on NGCon. Why? I told you upfront that this is the only exception because it is going to serve us well in PE power. Right? Circuit analysis, we went very deep, right? The virtual node and the super node and this and that, you know, why? Because it's going to serve you well in PE power. The Thevenin circuits, you think that you're done with them? No, they're going to make an appearance when we are discussing the equivalent circuit of synchronous machines, transformers, you know, induction machines, and so on and so forth, even for transmission lines. Okay, so same thing with power systems. We went really deep in power systems. Okay, knowing that all of that is going to help us in electronics and, you know, goes on and on and on. So circuits, I think if you have gone through the on-demand content, if you attended the live training program and you have done the homework assignments to the best of your abilities and tried to understand these concepts, you are probably over prepared. So I'm not too worried about it, but just don't make stupid mistakes. Okay, don't make silly mistakes, right? Don't just casually change the signs from positive to negative. Implement the KCLs properly. Identify what is a voltage gain. A battery does not always result in a voltage gain. It depends how the current is flowing through it. If the current is entering the negative terminal and leaving the positive terminal, that is a voltage gain or a voltage drop. Voltage gain or a voltage drop. Voltage gain. And if the current is entering the positive terminal and leaving the negative terminal of the battery, that is a voltage drop. So just because you see a voltage source does not mean that it will always result in a voltage gain or voltage. It was always result in a voltage gain. So it really depends. Okay. So enough said about circuit analysis. Super important topic. Linear systems. It's one of those, you know, there were 3 topics that we categorized together, right? Linear systems, communication, and signal processing. Heavily math intensive, right? But totally doable. So let's rate this. Frequency transient response. How do we rate frequency transient response? Transient response, guys. RLRC, medium. Okay, let's call it medium. Resonance, series resonance circuits, parallel resonance circuits, quality factor, bandwidth, easy. Transfer functions, they don't really make a super important appearance in here. It's mostly controls in the S domain, Laplace domain. But I would say, yeah, we have to, what was the most important thing about transfer functions? We had to bring them into standard form, S plus 1, right? Whether you have S in the numerator or in the denominator, we had to have a plus 1 beside it. So we had to pull constants sometimes. I would say it's easy. And then you basically can determine the dB gain and whatnot. Laplace. Now, a lot of students are scared of Laplace, but hopefully after going to the live training session, after understanding that we're not going to be using the integrals nearly as much. 95% of the cases, we don't use integral. We use the Laplace transform tables, right? And we work through all the different variations, all the important, these Laplace transform pairs. So how do we rate it? Right now, I have a split between easy and medium. Okay, let's call it a medium. Okay. Frequency transient response, or it repeated itself. So I think these are repeating. That's it. Okay. So overall, sort of half and half between easy and medium. I agree with this. Now, with linear system, I would say that if you systematically work through this stuff, to be honest, it's relatively easy. I know it sounds a little bit intimidating, especially if you haven't done these transforms in a while, but inverse Laplace transform, partial fraction expansion shows up again in Z transform, a lot of overlap. You have to sort of lay that groundwork, right? But a lot of overlap, a lot of synergy between Z transform and relatively easy transfer functions, I already pointed out. Now, the transient response can be a little bit tricky. Why? Because it really involves circuit analysis more than anything else. Those equations are fairly simple, the big fat V and V naught and VC of T, remember? So how the switching is happening, the before and after pictures, right? The one with the sad face and the one with the smiling face, right? So very important to create those before and after pictures for the transient analysis. When you go through it systematically, I'd correctly identify the initial conditions, I think it's very manageable. I'm not saying it's an easy section, but to be honest, it's not as difficult as students generally think. Okay, that's my take on it. You do need to invest time and effort into it, but it is not like computer networks where you have 25 lectures and you're preparing for 4 questions, right? Over here, you have actually very limited number of lectures. I don't remember the count, but it's probably 8 lectures maximum, and you can get up to 8 questions. Okay, so the effort to reward ratio is there. And RCRL transient, we went in a lot of depth. In fact, I took some of my slides from my P Power course when I was explaining you guys RCRL transient. You guys remember that? How the capacitor stores charge in the transient state, despite there being an open circuit, right? And the water wheel example for inductor, how it continues on with the kinetic energy, right? So we went in a lot of depth.